All right, so let's do a couple more examples thinking about transformations. So for each of these, we're going to sketch a graph of the given transformed function. Okay, so when we're sketching graphs of transformed functions, we're going to think about kind of two major things. One, we're going to figure out what the basic untransformed shape is. We're going to apply the transformations to get a sketch of the transformed function. Okay, so to start with, let's think about the basic shape of number one here. So what's the basic shape, or what's our untransformed graph? Well, this is a quadratic or squared graph. So our basic shape before we transformed it would be the shape of the x squared graph. And the x squared graph is a parabola. So there's our basic shape. Now, in order to sketch the transformed graph, we need to think about what transformations, thinking reflections, shifts, and stretches, have been applied. So let's look at our equation and see if we can figure out which transformations have been applied here. We've got a negative out in front. That's an x-axis reflection. A multiplier outside is a vertical stretch. And remember, if it's bigger than 1, it's going to be a stretch, meaning our function is going to get taller and skinnier. Smaller than 1, it's a compression, meaning we're compressing our function down. A negative 3, that's inside, or minus 3 inside with the x, that's a horizontal shift, right 3. And a plus 4 outside is a vertical shift, so that's up 4. Okay, let's see if we can apply all of those things. So we're going to take this basic shape. This has a vertex, or kind of starting point right here at 0, 0. We're going to shift it right 3, 1, 2, 3, and up 4, 1, 2, 3, 4. So there's our new vertex. We've reflected this. That means this is going to open down instead of reflecting up. And we've also stretched it. So it's going to be taller and skinnier than it was before. So there is my sketch. Now, just for fun, even though it wasn't asked, let's go ahead and find the domain and range of this graph. Okay. The domain is our x values. This is going to eventually expand and hit all x values. So our domain is negative infinity to infinity. Our range is our y values. That's going to be everything below 4. So how do we say everything smaller than 4? Negative infinity to 4. 4 is included, so we're going to use a bracket at 4. Okay, so there's a sketch of our transformed function. Now let's look at our next graph. f of x equals 1/3 times the square root of x plus 4 minus 3. So again, the first thing we want to do is think about the basic shape. Okay, well, what is the basic function that we're transforming here? Well, we're transforming the square root of x graph, and the square root of x has this basic shape. Okay, so now we're going to think about what have we done to this graph, what transformations have we applied, and we're going to use those transformations to sketch the transformed graph. Okay, so what transformations have we applied? Well, we've got a multiplier here. This represents a vertical stretch or compression. In this case, it's a vertical compression. We're compressing this graph down. Plus 4 inside with the x is a horizontal shift, and that's a shift left 4. Minus 3 outside is a vertical shift, so that's down 3. No reflections in this one. So let's see, we're going to take this kind of starting point here at 0, 0. We're going to shift it left 4, 1, 2, 3, 4, and down 3, 1, 2, 3. That's where we're going to grow this function. A vertical compression means we're squishing this guy down, so he's not going to grow quite as fast as he did before. So there's our sketch. Now again, let's go ahead just for practice and find our domain and our range. Okay, our domain is our x values. We start having domain here at negative 4, and we're going to continue to have domain through all positive infinity values. We're going to start at negative 4 and go to infinity. Negative 4 is included, so I use a bracket. We never include infinity. Our range is going to start here at negative 3 and go for forever. We're going to start at negative 3 and go to positive infinity. Again, negative 3 itself is included, and we never include infinity. So there's our domain and range of that guy. All right, last example here. Last example. We want to sketch a graph of f of x equals 1 over negative x plus 6. Okay, well, let's think about our basic function shape. So our basic shape is going to be the shape of 1 over x. The 1 over x graph is our L curves in top left and bottom right. So there's our basic shape, okay? We're going to think about transforming that basic shape to get our the sketch of our transformed graph, okay? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, so let's look at what we've done to our transformed graph. So what do we have? We have a negative down here with the x. That's going to be a y-axis reflection. And we have a plus 6. That's going to be a vertical shift up 6. Okay, let's think about that y-axis reflection first. So here's our y-axis. When I reflect, this graph is going to come over here, and this piece of our graph is going to come over here. So those purple lines represent our y-axis reflection. In other words, when I go to sketch this, instead of drawing top right, bottom left, I'm going to do top left, bottom right. Okay, and that's because of the reflection. Now remember, when we're thinking of transforming rational functions, functions that have an x in the bottom, we're going to think also about our vertical asymptote. So this function has a vertical asymptote at along the y-axis. And how has that been changed? Well, this guy has been shifted up 6 and has a y-axis reflection. Neither one of those is going to change that vertical asymptote. Y-axis reflection, that's going to stay on the y-axis. Shifting up 6 just moves this line up, but it's still a line. Okay? We also think about our horizontal asymptote. This guy has a horizontal asymptote here at on the x-axis. And let's think about how that changes with our y-axis reflection and our vertical shift. Well, when I reflect across the y-axis, again, this straight line doesn't change. But shifting up 6 certainly changes this. This is going to move up 1, 2, 3, 4, 5, 6. So our new horizontal asymptote is going to be up here at 6. Now, what good does that do us? Remember, the whole reason we transform our vertical and horizontal asymptote is going to help us sketch. With our y-axis reflection, I wanted to sketch my L curves in the top left and the bottom right. So there is a sketch of my transformed function. Now again, let's go ahead and find the domain and range just for practice. Okay. Our horizontal and vertical asymptotes also help us with the domain and range. Our domain is going to be everything except this vertical asymptote. That is everything except 0. So I can think of that as negative infinity to 0. It's also the domain of this piece of our graph, union, that's the mathematical way of saying and, with the domain of this piece of our graph, which is 0 to infinity. Similarly for our range is going to be everything but that horizontal asymptote in this case. So that's going to be negative infinity to 6, union, mathematical and, with 6 to infinity. Everything except 6. All right, so there's some examples of using transformations to sketch graphs. All right, so we sketched functions based on their equation. Now I want to try and write equations based on a description of the transformations, okay? So 3 different examples. So first we want to write the equation of a cube root function reflected across the y-axis, shifted left 2 and up 3. Now the first thing we need to do is think about what type of function are we starting with? Well, we're starting with a cube root function. Cube root is this guy. So that's my basic function and I'm going to transform it. Okay, so first I need to do reflected across the y-axis. Well, a y-axis reflection is a negative inside with my x. So there's my y-axis reflection. Now I need to shift left 2. Shifting left 2 means I'm adding 2 inside with the x. And then I need to shift up 3. So there is the equation of a cube root function reflected across the y-axis, shifted left 2 and up 3. Now, let's do the next one. An absolute value function stretched vertically by a factor of 4, shifted down 3/2 and right 7/5. So first we need to think about what's our basic function. Our basic function, it says, is an absolute value function. So that's the absolute value of x. We're going to take the absolute value of x. We're going to stretch it vertically by a factor of 4. Vertical stretches are multipliers outside our function. So there's our vertical stretch of 4. Now we're going to shift down 3/2. Down 3/2 means I'm subtracting 3/2 outside of the absolute value. And right 7/5. Right 7/5, that's a horizontal shift. That's going to be inside with my x. I want to go right, I'm going to go minus 7/5. So there's our function. 4 times absolute value of x minus 7/5 minus 3/2. All right, last one down here. A 4th degree equation reflected across the x-axis and stretched by a factor of 3 and moved up 17, horizontally by a factor of 3. Okay, so basic function shape is 4th degree. 4th degree means x to the 4th. So there's our starting point. We've reflected across the x-axis. An x-axis reflection means we have a negative out in front. Okay, so negative out in front. A horizontal stretch. Horizontal stretches are inside by a factor of 3. So technically that's a compression. So horizontal stretch, so we've got 3x to the 4th, and moved up 17. Moving up is plus 17 outside of the parentheses. Oh, so there we go. There's our equation for that guy. Okay. All right. Now we're asked to write the equation for the transform function pictured below. So we're given a graph and we're asked to write the equation, thinking about reflections, shifts, and stretches or compressions. Well, the first thing we need to know is we need to identify what is the basic shape. Well, this is our V graph. Which graph's basic shape is a V? The absolute value graph. So we're starting from an absolute value graph, absolute value of x, and we need to think about what have we done to that. Now, our basic absolute value graph starts down here at 0, 0, and grows from there, okay? So one thing that we've done is we've flipped this graph upside down. In other words, instead of opening up, it opens down. What does that? Well, an x-axis reflection. So this graph has an x-axis reflection. It's also been moved. It's been moved to the right 1 and up 1, 2, 3, 4, 5. So this graph has been moved right 1 and up 5. Okay, so that takes care of reflections and shifts. What about compressions or stretches? Well, compressions and stretches are a little bit harder to determine, but one thing that's helpful to think about is my original absolute value graph has the point 0, 0, and also the point 1, 1, and negative 1, 1. In other words, it goes over 1, up 1, over 1, up 1. There's that 1-to-1 ratio. This graph, starting here, also has that 1-to-1 ratio. I move 1 and 1, 1 and 1. That actually tells me this has been neither compressed nor stretched. So this is everything that I've done to my absolute value graph. I've reflected it across the x-axis, I moved it right 1, and I've moved it up 5. Let's see if we can write the equation that would do that. X-axis reflection is a negative out in front. Right 1 means I want to go minus 1 inside with the x. Up 5 means I'm going to add 5 on the outside. So here is our equation. F of x equals negative absolute value of x minus 1 plus 5.